Greetings, ladies and gentlemen. It gives us great pleasure to participate in the iconic 2020 conference. And on behalf of my co-authors Jonathan and Shadrach, allow me to take you through the title of our paper. The title of our paper is none other than Optimized K-means Clustering Algorithm using an intelligent stable plastic variational autoencoder with self-intrinsic cluster validation mechanism. So that's the title of our paper. So next I'll take you to the abstract. And in the abstract, what we are saying is that the clustering is one of the most important tasks in the exploratory data analysis. And among the family of machine learning algorithms, those that specifically do clustering, K-means happens to be the most famous because it's easy to implement, it's computationally more efficient, and of course it's easy to understand. But the main challenge here is identifying the number of K, which has to be input by the users. And of course, several variants of the K optimization techniques have been proposed since the K-means was invented. And the objective of this paper is therefore none other than to analyze now those techniques that have been proposed and create those as the foundation of now coming up with this other more enhanced K optimization technique that we're talking about. In the introduction, we are saying that clustering is one of the important unsupervised learning in data mining. Of course, we are trying to gain a deeper insight into a set of unlabeled data set. But finding the right number of K has always been a trial and error process. Very, very important to note that clustering is not something small. It's a huge thing with a long and rich history in anthropology, biology, medicine, psychology, statistics, mathematics, engineering, and even computer science. So it's not a small thing when you talk about clustering. Okay? So it's a very important thing when you talk about clustering. Okay? So we'll also tell you how the rest of this presentation proceeds. Related works, proposed algorithm, results and discussion, and lastly on conclusions. So related works on K optimization techniques. So what do we mean? This is what we mean. That since the invention of the K-means clustering algorithm, and it was noticed that the value of K, or selecting the value of K, is a problem, then researchers have been solving this problem. And these are some of the techniques that researchers have come up with to solve now that problem of K-means in terms of now selecting the K. So we have CV++ all the way to K star algorithm. We have got enhanced parallel K-means, interactive K-means minus approach, and all these have been discussed in the article more. Next, we also have K star means, improved K-means clustering with Atkinson index to classify liver patient dataset. We also have the technique for integrating K-means with the elbow method. Elbow method is one of the traditional methods of trying to find a right value of K. Very important and helpful in trying to do customer segmentation. You remember, customer segmentation is a business strategy, trying to cluster customers in different levels so that you get a good product that suits them. Seed selection algorithm through K-means, and the last one is bisecting K-means algorithm. Next, we have a-means. All these are variants or basically K optimization techniques that have been proposed by other researchers. We also have new initialization performance measure for the rough K-means. Boundary weighted K-means algorithm, G-means. We also have a hybrid model using Leech and K-means clustering algorithms. We have got X-means and improved K-means clustering algorithm based on an adaptive initial parameter estimation procedure for image segmentation. So very important to understand that the goal of all these variants, very interesting, that all these variants were geared towards improving on the selection of K. Next, we looked at how much have autoencoders been applied in feature mining, because we felt that the data on the autoencoders embedded latent space can give a hint on the value of K. And to start off, we are saying autoencoders are basically feed-forward neural networks that reconstruct output from the representation of a compressed lower dimensional code. So autoencoders are known for providing effective ways of learning good representation from large amounts of unlabeled data, and this is very critical. So the review of application of autoencoders in feature mining and learning representation will always reveal ways that can guide in the selection of K in the K-means clustering algorithm. So we looked at a few ways in which autoencoders have been applied in mining features from an unlabeled dataset. And we were saying previously, autoencoders have been applied to adaptively learn a suitable feature representation from a set of unlabeled data. They have also been used to improve learning, which is very critical for unsupervised machine learning algorithms. Extracting high-level features which are relevant. Remember, from a given set of unlabeled data, you don't want to capture everything. You want to capture high-level features which are important and which are more relevant. So they have been, autoencoders have been applied in all this, and even learning efficient and compact representation of health data for diagnosis. Okay. So based on now how autoencoders have been applied in the feature mining and learning representations, we thought we could now leverage on that and create a K optimization model that is more efficient. So if you look at my flowchart here, after starting, unlabeled dataset is input, and very critical process is process 1, where we are mining features from the unlabeled dataset. We are trying to learn representations, of course using the stable plastic variation autoencoder. After that, it generates a hint of the value of K, which now we input into the K-means clustering algorithms, which now generates the clusters. And we're asking ourselves, is the quality of clusters optimal? If yes, it stops. If no, it goes back and the process is repeated until we get good quality clusters. Next is basically a pseudocode now based on that proposed model. And after starting, what we are saying is that now the set of unlabeled data is input into the plastic variation autoencoder. Okay? And what is the stable plastic variation autoencoder doing? It's trying to mine features, high-level features, as we said, from that set of unlabeled data set. Is learning representation. Okay? And all this information is mapped onto the autoencoder's embedded latent space. Okay? Then that becomes the hint of the K. So after that, K now is automatically captured by the K-means clustering algorithm. Okay? But after the K-means clustering algorithm generates the clusters, we are taking through those clusters through a cluster validation kind of check. Okay, so next one, the biggest question probably most of you would ask us is, why are you using why stable plastic? Very interesting. But stable plastic variation autoencoder is basically assisting us to achieve stability without rigidity and plasticity without chaos in our model. And as you all know, or most of you may know who have dealt with a lot of machine learning algorithms, we are saying premature convergence may occur when the weights and bias of the autoencoder settle in a state that is only optimal at a local level. And when it misses out on global minima of the entire multidimensional space is a problem. At the same time, overfitting may occur, which is a state of where the autoencoder becomes highly tailored to a training dataset at a fine grain level, and it becomes unfit, rigid, and less adaptable for any other test data set. So that's a problem, and we don't want that. Okay? So in the results and discussions, one of the things that we noticed during the literature review is that optimization objective in clustering algorithms can be achieved in mostly three ways. And one of it is combinatorial optimization. And a very good example is the greedy search. Quite a number of greedy algorithms have been proposed in machine learning. Another optimization objective achievement is through combinatorial optimization. Okay, then convex optimization. An example is the gradient descent. And lastly, constrained optimization with an example of linear programming. So the foundation of our proposed algorithm is actually combinatorial optimization. Okay. So when we were trying to do some experimentation with our developed algorithm, we looked at the Sulhut index, the time of execution, and the number of iterations for the k value. Okay, so those are what we used during the comparative evaluation. And Sulhut value, as you know, it borders -1 and 1. And it measures how similar an object to its own cluster is compared to other clusters. So we are talking of cohesion and separation. That's all about clustering. So the proposed K optimization technique demonstrated higher Sulhut values. So when the Sulhut values are high, then you are trying to say the clustering is better. Of course, lower time of the execution and lower number of iteration, that means this model was more efficient. Okay. So we did this compared to a few techniques because, of course, we didn't have time to test it with all the others. Next thing is conclusion and recommendation. And in the conclusion and recommendation, we are saying that it's very clear that K optimization technique is a subject with growing research interest. And I think that explains why we are doing this, because it has attracted a huge number of researchers. But again, looking at the autoencoders, there is basically no research that leverages on the information from the autoencoder. We notice that the information from the autoencoder can guide in the selection on the value of K. So no research, little research, that would leverage on that. Remember, leverage is a point that when it's touched, it can create chaos, or the impact is going to be very high. So leveraging on autoencoder to give a hint on the value of K is something that we thought of and can be a whole game changer. Okay, so experimental results of code showed that the developed model performed better. We looked at only 3 because it was hard to experiment with all the other techniques that we reviewed at the literature level. So with those very few remarks, we want to really thank you for listening to our presentation. And more information, you can have a look at our article. Thank you. Greetings, ladies and gentlemen. It gives us great pleasure to participate in the iconic 2020 conference.